looks like this. If this is 0.1 omega 1, and this is omega 1, and this here is 10 omega 1. The straight line Mohr diagram of phase, so we'll label this as phase, is 0 degrees, right, since we're doing phase, 0 degrees all the way up until 0.1 omega 1. And then it increases at the rate of 45 n degrees per decade. So let this upper limit here be 90 n, okay, from 0 to 90 n, and let me do this and this. In between 0.1 omega 1 and 10 omega 1, it will increase linearly. Not very good. Okay, like that. And the slope there will be 45 n degrees per decade. And then it will flatten out. Okay. Last time, what we did, we plotted the exact phase versus frequency on a logarithmic scale, and what it looked like, it was going below that line, and then above that line, and then settling out. Okay. So we can use these to draw the straight line Bode diagrams for given various transfer functions. Are there any questions, first of all, about these here? Also, let me say that this constant is along either the positive or negative real axis. A factor like this, S over omega 1. And remember, what we're doing is plotting the frequency response function. So, in effect, what we're actually doing is replacing S by j omega. Okay, so here, if we're just looking at the inside here, we have j omega over omega 1. And that's purely imaginary. Okay, and so it can be depicted along the positive imaginary axis. In other words, positive imaginary axis. And so you can say here j omega over omega 1. Okay, and you draw a vector. Just like here, you draw a vector from the origin to the positive real number or to the negative real number. Right here, you draw a vector up to the point there, and it's clear that the phase is 90 degrees, right? And so it's 90 n in the more general case. And then the magnitude clearly is increasing as omega increases, right? It's just that this vector gets larger and larger, and this depicts the change in the magnitude as the frequency increases from the lowest to the highest frequency. Okay, and then here it's useful again to draw a little vector diagram, right? And so we have replacing S by j omega, we have 1 plus j omega over omega 1. And so we have here, we have this, and we have the angle theta in here. The angle theta, what you can see is that if omega is equal to 0, that vector is along the positive real axis, and so it has 0 phase. Right? And that's what this is depicting here, 0 phase. Right? And then as theta increases, the phase is approaching 90 degrees. Or for the case in which we have it's raised to the n, it's 90 n. Okay. So this diagram is very helpful in showing you the limits on the phase, right? From 0, when omega is equal to 0, to 90, when omega goes to infinity. Okay. And, yeah. So how about the case in which we have a second quadrant factor of this form? In other words, if you have minus 1 plus s over omega 1 raised to the nth power, right? You know, you can draw the vector diagram. You've got minus 1 and j omega over omega 1. So you've got in that case this and this. What you can see here, what does the phase, oh, first of all, magnitude-wise, magnitude. In fact, regardless of whether we're considering a point in the first, second, third, or fourth quadrant, and here we have a point in the first quadrant, second quadrant, here j omega over omega 1 is a third quadrant, and the fourth quadrant here. Okay, well, this is 1 minus 1. And what is the magnitude of any one of those vectors equal to?
Same. 20 NdV.
Huh?
20 NdV.
In terms of the Pythagorean theorem.
It would be 1 squared.
Yeah, 1 squared.
Omega
1
over omega 1 squared. And take this.
Okay, so any one of these, in other words, you have plus or minus 1, plus or minus j, and let me put it this way, plus j plus or minus omega over omega 1. What is the magnitude of that equal to? Square root of the magnitude of plus or minus 1 squared plus the magnitude of j plus or minus omega over omega 1 magnitude. And so that's just equal to the square root of 1 plus omega over omega 1 quantity squared. The point here is that the magnitude is exactly the same for each quadrant. Okay, and so this is what the magnitude looks like for factors of this form, plus or minus, plus or minus. Okay, it doesn't matter about the sign. It could be first, second, third, or fourth quadrant vector. Okay, so now as far as phase is concerned, what we saw is for a first quadrant vector, the phase varies from 0 to 90 degrees as the frequency increases from 0 to infinity. Okay, and this is the straight line approximation. There is a 90-degree change from low to high frequencies. Or more generally, if it's raised to the nth power, it's 0 to 90n. Okay. How about the second quadrant? What does the phase begin with at low frequencies, and what does it end up with at high frequencies?
180 and then goes to 90.
From 180 to 90 degrees, right? So, and it's going to vary by 90 degrees from low to high frequencies, right? And so we can draw the same kind of straight line Bode diagram of phase for the second quadrant, the same kind, but it's going to start at 180 and end up at 90, 180n to 90n. Okay, so for this, one here, minus 1 plus j omega over omega 1, omega 1, yeah, raised to the n. The Bode diagram of magnitude looks like that. Bode diagram of phase looks like this. We have, remember, 1 decade below omega 1, and 1 decade above omega 1. It's going to start out at 180 and end up at 90, right? So let this be here 180, or more generally 180n, okay? And this 90 n. So you go across like that and put these in here. It's going to start out and let me move that. It's going to start out at the 180 n at very low frequencies. It's going to end up at 90 n at high frequency, and in between, it's going to do this, right? Like that. And the slope, just like the slope is 45 n here, what is the slope going to be here?
Negative 45.
Minus 45. Minus 45 n degrees per decade. Okay. And so we see this purely by inspection of the vector in the second quadrant as the frequency increases from zero to 90, from 0 to infinity. Phase going from 180 to 90. How about the third quadrant? What?
180 to 270.
180 to 270, right? Or you could say minus 180 to minus 90, right? The same thing, right? So you've got minus 1 minus j omega 1 raised to the nth power. And this, put that 180 n, right? At low frequencies, 90 and at high frequencies. Here, a similar kind of thing. We said it's going to go from 180 to 270, right?
Or negative 180 to negative 90.
Okay, so let this be 0 degrees. Let this be minus 180 n, and let that be minus 90 n. So we put that in, and this in, and this, and this. And this is 0.1 omega 1. This is omega 1. That's 10 omega 1. Okay, so at n, we also need this one in here. So minus 180 to minus 90, isn't that right? So it's going to be at low frequencies starting out here. Okay, in other words, from the lowest frequency, comes up constant up until that point. And then it's constant beyond 10 omega 1. And it's linearly increasing, and the slope is obviously positive, so it's 45 n degrees per decade. Okay. We could go through a similar analysis to what I did here for the first quadrant vector and get the exact Bode diagrams of magnitude and phase, but I don't think it's necessary. Okay. You would get the similar kinds of plots, okay, for the exact plot, and then you approximate the straight line, approximate by a straight line. And then for the last one, how about the fourth quadrant? The fourth quadrant varies from what to what? As the fourth quadrant vector varies from what to what as 0 to minus 90, right? Or 360 to 270. Yeah. So you've got that. Another way to put it down here. And just extend these. And this would be 0 degrees, and this would be minus 90 n. Right, and extend this across, and I have another one in between. Sorry, 0 minus 90, right? And so, yeah, so we don't need that in between. just need this line extended down, this line extended down. This is 0.1 omega 1, this is omega 1, and that's 10 omega 1. Okay? And so 0 at low frequencies, by observation of this vector, starting at, with omega equals 0, has 0 phase. As omega increases, the imaginary component is getting larger and larger, and so the vector is tending to point downward, and that's minus 90 degrees. So it starts out here and it ends up there, and it settles out there. Right, and this clearly has a phase of minus 45 n degrees per decade. Okay, and any question about this? Like I say, it's useful to look at the little vector diagram here. Okay, just like we did all the way across. Right, we looked at this vector diagram for positive and negative real. This vector diagram is purely imaginary. It's pointing up. Okay. And then this vector diagram for these other ones here. So the magnitude doesn't change regardless, right? If you have this form here, the magnitude, straight line vector diagram, the magnitude is the same. Okay, and then I should get into a few examples now. There's the quadratic factor also that we want to consider. The quadratic factor, you see, if you multiply two linear factors together, say 1 plus s over omega 1 and 1 plus s over omega 2, then the damping ratio will always be greater than 1. Okay, you can show that. But if you have a quadratic factor in which the damping ratio is between 0 and 1, you will not have real roots. Like the roots here are real, right? If you set this to 0 for that to 0, you get real roots. If you have a damping factor for a quadratic factor, if you have a damping ratio between 0 and 1, you cannot separate it into the product of two factors, each of which has real roots. Okay, the roots will always be complex. When the damping ratio is between 0 and 1, the roots are always complex. Okay, and so I'll go ahead and take care of that one while we're at it here. And oh, by the way, if n is negative, right? What does the phase plot look like in that case? If n is negative, right? If n is negative, it's going to be let's say n equals -1. The phase, this is what we call it slope, is going to be plus 45, right? So it's going to go from, if n is -1, it's going to go from minus 180 to minus 90, right? Upward. Okay. Same thing for any one of these, right? If n is negative, right, it's going to go downward. So really, and so in other words, if you have n equals -1, and all right, -1 there, right? You take a look at what the phase is doing for any one of those factors, right? And you just take the negative of the limits, right? In other words, the negative of each of those, right? And negative, and so it flips. The phase flips. Let's say the slope flips, and then the limits just become the negative of what they were. The limits on phase from low to high frequencies. Okay, so let's now take a look at, are there any questions about that point? No. Okay, so let's take a look at the quadratic factor. quadratic factor might look like this. You have, you have omega n squared over s squared plus 2 theta omega n s plus omega n squared, where the damping ratio is between 0 and 1. Right? If it's between 0 and 1, you have complex conjugate roots, and so you can't put it into this form where you have real roots. Okay, so in this case, well, again, we're interested in the straight line approximation. And then the error in that straight line approximation will depend on what the damping ratio is. The way to determine or to come about the straight line approximation is regardless of what zeta is, regardless of what it actually is, and I'll show you an example in a second, you assume zeta equal 1. If zeta is equal to 1, then this becomes a perfect square. Okay, and in other words, you have omega n squared divided by s plus omega n quantity squared, right? Because you get s squared plus 2 zeta omega n plus omega n squared, so the zeta is equal to 1. And this can be written as 1 over 1 plus s over omega sub n quantity squared, right? If you divide top and bottom by omega sub n. And so this, we already know how to take care of it, right? In other words, this, if you want to express it as a numerator factor, it's 1 plus s over omega 1 raised to the minus 2. Okay, and so how do you plot the straight line Bode diagram of that? Right? It looks like it falls into this form here, where n is minus 2. Okay, straight line Bode diagram of magnitude will be composed of a straight line that goes from along the 0 dB axis up until omega sub n there, right, instead of omega 1. And then, sorry?
Down.
It's going to go downward with a slope of what? Minus 40, right? Because n is minus 2. Right? So it's 20 times minus 2, so it's going to be going downward at the rate of 40 dB per decade. So the straight line Bode diagram of magnitude looks like there's 0 dB, and at omega sub n, it's going to break downward at the rate of 40 dB per decade. So that's the magnitude there. And how about phase? Phase, again, we can use this right here, right? Our n value is minus 2, so this is going to be minus 90 degrees per decade, downward. So it's going to start at the 0 degrees, let that be 0.1 omega 1, and this here, omega sub n, sub n, and so and it's going to go like this, and let this be this level. This is 0 degrees, and this is minus 180 degrees, right? And this line across down, and this is 2 decades, right? The 0.1 omega 1, omega 1, and 10 omega 1 is going to decrease at the rate of 45 degrees for each decade. So over 1 decade, it's going to get up to there, and over 2 decades, it's going to get down to there. Okay. Is that true? What is the slope? Minus 90 degrees per decade. Right, so after 1 decade, it's going to get down to minus 90 degrees. and after 2 decades down to minus 180. So it's going to go like that, and then it's going to flatten out. Right. So that's a straight line Bode diagram, magnitude and phase. And if you take a look at the book there on page 411, it has Bode diagrams of magnitude and phase of such a of such a quadratic factor, the exact Bode diagrams of magnitude and phase. And what you see is that they don't look like straight lines, right? They do depend on what the damping ratio is, right? If the damping ratio is very small, then you get a peaking. You get a peaking there, okay? And likewise, if the damping ratio is very small, you get instead of decreasing like this one here, it's gonna bow upward and then bow downward like this, okay? Let's see. Yeah. Kind of like this and like that. Okay, so and then here, but it really depends on what the damping ratio is. Okay, what if you have an example here of I have 2 over s squared plus 2s plus 2. Okay, and we can determine this can be approximated by 1 over 1 plus s over square root of 2 quantity squared. Okay, if you assume zeta is equal to 1, right? It follows, in other words, it follows this form here. Okay, and the omega sub n is equal to the square root of 2, right? Because this is compared to that. Okay, and what is the actual damping ratio here? The 2 zeta is what we're looking for. The omega n, which is the square root of 2, is equal to 2. So the damping ratio is 1 over square root of 2, 0.707. The 0.707 looks a bit like this. Try to draw that in there. Straight line and straight line. It just comes up a bit, and then it goes down like that. That's the exact Bode diagram, right? For the case in which the damping ratio is 0.7. Okay, and for the exact Bode diagram of phase looks something like this one here as well, right? So you've got some error. As that damping ratio gets smaller and smaller, the actual damping ratio, you're going to have a greater peaking, right? It's going to peak upward and upward like that. Okay, and then here you get more bowing outward and like that. And so one of these homework problems I have given you is asking you to approximate the error, the maximum error in magnitude, I believe, between the exact and the straight line, right? So what you need to do there is determine the approximate the exact phase and exact magnitude, and then compare it to the straight line. Approximate by looking at those diagrams, these diagrams here. If you just take a look at them, you can eyeball the amount of error. Okay, so that's what I'm asking you to do.
So we can like put those in that map.
Sorry.
So we can like put them in that the actual map.
You can draw you can actually draw it using MATLAB, right? And then you can use the cursor to find the magnitude at
That's okay for the homework.
where the maximum error occurs.
That's okay for the homework, though, we can use that.
Sorry?
That's okay for the homework, we can use that.
Yeah, you can use that, right. I mean, that's good.
Is that like a file you have on web courses or something? Or is that like,
This one here,
yeah?
That's
Is that a
page
general
411.
sheet? Oh.
that's page 411.
Oh, okay, it's in the book. Got it.
Right, or you can do it with MATLAB. You can
Okay.
draw the exact Bode diagram using MATLAB.
Yeah, and then you said find the peak and
You
and then
find the
just
maximum
compare to
error.
that.
I think that's what it's asking for.
Okay.
Okay, let's do some examples. And see this example here I have. And, so a lot of these things that I've written here are pretty much common sense. Okay, you can remember this. If you have a factor of this form here, all you have to you know that there's no slope change. It goes through 0 dB at omega 1. Okay, 0 dB at omega 1. So you're given this, or this is part of the transfer function. You know what n is, you know what omega 1 is, and so you can draw the exact Bode diagram of such factors for any given omega 1 and n. And similarly, if you've got a constant, you just take 20 times the log of the magnitude, and the phase is going to be either 0 or 180. And here again, if you have a factor of that the form 1 plus s over omega 1 raised to the n. What you really have to remember is that magnitude-wise, it's 0 dB up until omega 1, and then it increases at 20 n dB per decade. Phase-wise, you have to remember that the break frequencies are 1 decade below omega 1 and 1 decade above omega 1. Okay, and that clearly from the diagram it goes from 0 to 90, or in the general case 0 to 90 n. And the same reasoning here for any one of these vectors, second, third, or fourth quadrant. Pretty much reason that out. Okay. When you have a transfer function like this, h of s is equal to 10 over s plus 10 over s plus 100. Okay. So the first thing to do is put it into that time constant form. In other words, it could be. See, it could be let me write over here. A constant. You could have something of the form s over omega 1 raised to the n. You could have something of the form plus or minus 1 plus or minus s over omega 1 raised to the n. These two omegas, this is called omega 2, just to distinguish the two that are not the same. And you can also have a quadratic factor of the form that's given here. Okay. And of course, this right here can be expressed as 1 over 1 plus 2 zeta over omega 1 omega n plus s over omega n quantity squared. Right? In other words, divide top and bottom by omega n squared. Yeah. It puts it into a kind of so-called time constant form. These are time constant form here. Okay, this one, the first thing to do is put it in time constant form. What we're going to do here is factor out 10 in the numerator, factor out 100 in the denominator, and so we would get 100 over 100, so that it's just s over 1 and 1 plus s over 10 over 10, 1 plus s over 100. Okay. 10, yeah. Okay, and see, the other way that we can put it into this form, s over 1 raised to the minus 1, 1 plus s over 10 raised to the first, and 1 plus s over 100 raised to the minus 1, right? So that's the way I presented them, okay? And so you attack each one, right? You can draw the straight line Bowie diagram for each one. And, you know, you can start with this one, and notice, remember, this one, the slope doesn't change. Slope doesn't change. And so you've got the 0 dB line. This is 1. And so the slope is what? Positive or negative? Positive or negative?
Negative, yeah.
And what is the slope? Minus 20 dB per decade, right? So it goes something like this, right? Where this is minus 20 dB per decade. It goes through 0 dB at what frequency? 20. That's that right there. And yeah, see this you can express it as 20 n, where n is minus 1, right? And then the other next factor there is this factor there. It's going to have a break frequency of 10, and then the next one over there has a break frequency of 100. So, you know, we start out with 0 dB. I mean, it's possible to draw each one of these on the same set of axes, on the same axis, right? But I'll do it first here on separate axes. And if this one if this is 10, right? And this is 10. So it goes out to 10, and then what does it do? With that factor,
It goes down with the slope of negative 1.
breaks down or
Oh, it's all yeah.
that one, the break frequency is 10, and n is equal to 1, so it breaks upward, right? Upward. And then you have the third one in there. It is at 100. And it breaks downward, right? And it's, in other words, it's 0 up until that point there. So this is 0 dB. So we have these three, and what we're going to do is add them up, right? That was originally because we had products. We took the log that became the sum, okay? And so this one, it continues, right, from the lowest frequency to the highest frequency. That has no slope change. And so the composite, say, here, this is 1, is coming, there's no contribution from these two, 0, right? And so it's coming downward, and it continues downward until it sees a slope change, right? And in fact, this is how we can plot these Bowie diagrams, at least of magnitude, based on slope change, right? So we have this coming downward until we get to there. And then the slope is increasing, right? It goes from 0 dB per decade to 20 dB per decade, right? And that is going to cancel the slope of this one. And so at that point, it's going to flatten out. And then at that frequency, what happens?
It goes back down again.
The slope changes, it decreases by 20 dB per decade. So it's going to go down like that, right? So it's got a slope of minus 20 dB per decade up until 10 radians per second. and then it flattens out, so it has zero slope, and then it has a slope of minus 20 dB per decade. How about the phase? Phase. What does that look like? Again, we can just use these here that we had. The phase for the first vector. Okay, before I get to the phase, you can basically draw the straight line Bode diagram, the composite down here, basically by inspection, right? You know that you've got a factor that goes through 0 dB, 0 dB at 1 radian per second, right? And then you see at the next, at the break frequency, the next break frequency, which is 10, is going to, the slope is going to change positively, right? So it's going to go from minus 20 to 0 slope, and then at the next break frequency, 100, the slope is going to change, the slope is going to change by minus 20 dB per decade. So you can draw this by inspection. Okay. Phase-wise, this factor here, what is the phase of the factor, this factor here?
Minus 180.
Remember, it's 90n, and n is equal minus 1, right? The phase is constant, right? It's along the positive imaginary axis, right? So that's 90 degrees. So this is minus 90, right? So the first 0 degrees contributes minus 90 degrees. That's for this factor here, right? So the S over 1 raised to the minus 1. That's what the phase looks like. The phase for this factor, remember, 1 decade below would be 1, 1 decade above would be 100. It's going to break. Being a numerator factor, it's going to break upward or downward? Upward. At what frequency? Keep in mind, when you're dealing with phase of such factors, you have to think 1 decade below and 1 decade above that break frequency. So it's going to break upward at, let's see, let me make this, yeah, 0 degrees. And let this be 1 decade below, 10, and 1 decade above. Okay. It's going to break upward at 1, linearly increasing until 1 decade above it, which is 100, and it's going to flatten out. So this is 90 degrees. Okay. And then this one here looks like this, except 1 decade below is 10, 1 decade above is 1,000, and the break frequency is 100, not 10. Okay, so if you draw this, let me put it up above, like this, let that be 0 degrees, and so here's 10, 100, and 1,000, okay, and at 1 decade below this, in other words at 10, it's going to break downward at the rate of 45 degrees per decade. So 0 up until that point, and then it breaks downward until 1 decade above that, and it's going to flatten out. Minus 90 degrees. And then all we have to do is draw the composite, right? So this one, we start very low frequencies, this is the only one that contributes phase at minus 90. These contribute 0, 0. So it starts out at minus 90. Let's see what this is. Let this be 0 degrees. Starts out at minus 90. Let that be minus 90 degrees. And then at this point, which is 1, right, it's going to break upward because you can see that it does break upward. And yeah. So it's going to be minus 90, and it's going to break upward. And at 10, it's going to flatten out. So it gets up to minus 45 degrees. So at 10, you see this positive slope is canceled by that negative slope. The net slope will be 0 until the next break frequency, which is right here. So it's constant until that point. And at that point, the slope change is what? Positive or negative slope change at that point? It goes from 45. It goes from 45 to 0. So slope change is negative. Okay. So it goes from 0 slope until 0 slope to minus 45 degrees per decade slope. Right. This is going downward. Okay. And until it gets to this point here, where you see, is the slope change positive or negative at that point? Well, you say, okay,
Positive.
this slope is minus 45. What's the slope of that?
0.
So the change in
Positive.
slope is positive, right? So it goes from minus 45, this one is minus 45 degrees per decade. It goes to 0. It flattens out. In other words, it ends up at minus 90 again. Okay, so this is the straight line bow diagram of magnitude. This is the straight line bow diagram of phase. If you did this with MATLAB, you get nice smooth curves, right? But these straight line curves would pretty much match. In other words, you'd have something from the MATLAB that looks kind of like this. Right. That's what MATLAB would do. Now there's a way to check. Yeah.
Just explain again real quick why that SOFR 100 term doesn't break away at 100, it breaks away at 10.
This factor here. Yeah, because when we drew the straight line Boddy diagram, right, the straight line Boddy diagram, the magnitude breaks at 100, okay, but the phase breaks at 2 different frequencies, 1 decade below 100 and 1 decade above 100, okay, and that's what I've shown here, right? In other words, this factor, this is for the factor 1 plus s over 10, okay, and so this is here, and this is for the factor, the denominator factor, 1 plus s over 100 raised to the minus 1. Does that help?
Yeah.
Okay. And what we want to do is check our work, okay? if you take a look at the original here, you could look at this one, or you could look at that, but let's look at this one. Let's think low frequency and high frequency, okay? And in other words, you're replacing in your mind S by J omega, and you're letting omega be very, very small. That's essentially the same as letting S be very small. If S is very small, this S plus 10 factor can be approximated by 10, this by 100, and so at very low frequencies, basically what we have is 10 over S, right? Because this is this S in the numerator. This can be approximated by S. This can be approximated by S. They cancel out, so you just get 10 over S. What is the phase of this factor here? 10 over J omega. I replace S by J omega. This is minus 90, right? Minus J 10 over omega, right? Multiply numerator and denominator by J. This is minus J 10 over omega. Omega itself is positive. Therefore, this is positive. Minus J, the positive number, has a phase of minus 90 degrees. Okay? So, in other words, this can be depicted as a factor along the negative imaginary minus J 10 over omega. Omega is positive. And so, it starts out with a phase of minus 90 degrees, right? Which is what we see here. Starts out at minus 90 degrees. And how about for very high frequencies? Go back up to this one here. At very high frequencies, oh, by the way, I made a mistake as far as low frequencies are concerned. We go back to low frequencies. When omega is very small, or S is very small, this is 10, this is 100, right? So you just get 1 over S instead of 10 over S, right? But it's still true that this is still the same, right? Okay. So that was low frequency. S basically goes to 0. High frequency, what do you get? Now, this factor can be approximated by S, that by S. They cancel. You get now 10 over S. What is the phase of that? Minus 90, right? So it starts at low frequencies at minus 90 and ends at high frequencies at minus 90. So that's how you can check your work. Let's do some other ones here. So we can make one up too. Yeah, let's just make one up. So. Let's say H of S is equal to 1 plus S over let that be multiplied by 10, and let this be minus 1 plus S over 100. Okay. And now, anybody want to try that? Do that. Straight line row diagrams of magnitude phase.
rewrite it.
Once you raise it up, I mean, if you wanna put the composite down here, you might wanna.
I was gonna put it on the same graph.
Oh, that's fine, that's good.
You have different color? It's -20. Twenty plus 20 is 40.
It's flat.
So that's the magnitude.
Yeah, that looks okay. Looks fine. You wanna explain what you did?
Yeah, so there's 10 and 100 are the breaking frequencies. This one is a constant, so this is 20 log base 10 and 10. This is simply 20 for all the frequencies. The second one has a break frequency at 10, but it will be 0 until 10. Then it would increase at a rate of 20 per day. And the third one, basically the break frequency is 100, so it would be 0 until 100. And then it would decrease at a rate of -20 per day. In which case, if you forget this, this is basically the same as 20 log base 10, or the magnitude of this is alpha, to the -1. So you can bring the -1 out front, which means that the rate of change.
Okay.
The constant will be 0 phase. So this is 1, 100. It would be 0 for low frequencies. And it starts to pick up at 1. It's at the rate of 45.
Yeah, it's one decade below, right?
So it starts at 1, and it goes up. It goes up to 9. And that's the other one. The other one has a phase of 0. It would be 180, right? 180 all the way to 90. Really high frequency rate. So it starts at 180. You can also use negative 180 and then minus 9. Minus 9. Right?
From minus 180
Minus
to
2. Or that would be minus 270. Okay, so we go from 180 all the way to 90. There's a negative 1. So minus 180 all the way to
Just gonna slow it
minus
down.
90. So you
No, it's 180 to positive 9. 180 to positive 9.
Sure.
It's in the second quadrant, so it's 180 to positive 9.
There's a negative 1.
That just means it's negative 45 degrees per decade.
Okay. Low frequency would be 180 until we get to 10. And then instead of going to 90, you should go all the way to 270. Right? Because in general case, it will go down.
It'll do 135 at 100 and then 90.
But that would be without the negative.
So essentially, you've got 1 over the right? So in these angles, we do minus whatever the angles we have in positive. Is it really?
It's actually so. I simply grab these and then subtract them.
Well,
Subtract the
actually, you don't have to subtract, actually you just draw the straight line inverted diagram of each one. And like this one is going to start at, what did we say?
180.
Normally it would go from, as a numerator factor, 180 to 90 degrees, right? That's for this one here. And the denominator factor is going to be minus 180 to minus 90 degrees.
That's what I'm saying.
Usually you're right.
Everybody was saying that.
Negative 180.
Okay.
Okay, yeah. Or you can simply say that it goes from 180 to 90 and subtract.
You can say, you can add 360 to this, so you can say 180 to 270.
Okay. Yes, I was right. So basically it goes, it's 180 until 10. And then it was, instead of moving downward, it would move upward. I see. So this is basically 270.
Yeah.
So now simply the atom,
Yeah, you simply add them up.
basically 180, and then would increase at the rate of 45 degrees.
Yeah.
Until here. And then here would increase at the rate of 90 degrees.
Yeah, so you can't really show it here, right?
Here. 45. 90. Until we get to here. Oh, until we get to here.
To make
Then
these
it will
slopes a
basically
bit
become
small.
45 again. 45. This would be 1 decade. This one is 10. This is 100.
Yeah, but 100 is over here.
So basically 40 plus 40. This is a 90 degrees per.
Yeah, but I'm saying what you need to do is make these slopes actually
Well,
small.
you want it to match the scale?
Yeah, it has to be matching.
So basically, so this is 45.
It's just breaks here.
So that would be 45.
Yeah. Levels out. Right? That looks good.
It's not.
Can you kind of just summarize that? Actually,
Oh,
there's not a rush.
Okay, so basically, after we get every individual plot of the phase for every single factor here, we simply add them and start multiplying each other with the phase add. So from almost 0 all the way to 1, you only have a phase of 180 plus 0, 0. So that would be just 1. Then from 1 to 10, there will be a change of 20 dB. The slope of 45 degrees per decade added to the graph. So we're gonna add, basically, this, the angle will change at the rate of 45 degrees until it gets to 10. So basically there's a 45 degrees per decade. Then from 10 to 100, we got 20 dB here, and a 20 dB here, so 40 dB, which becomes like 45 degrees plus 45 degrees, so 90 degrees per decade, change from here to here. Then here, the regular graph had a 20 dB, so this is a 45 plus 0. That will be a 45 change. And then at the end, it flattens out, so 0 plus 0, 0 change.
Okay, good. And the lesson you can see, you can look at low and high frequencies. Again, for that S equals 0 for low, and what do you get? Minus 10. Minus 10 is a phase of 180 degrees, which is this. Right? How about at high frequencies? You throw away these high frequencies, you get 10. Okay. So ideally, you should be coming up to, at high frequencies, you throw away these, and you come up with 10, which is a positive real number. So ideally, this would come up to 0. If you did it, on scale axes, it would come up to 0. So I think the assignment is due on a Sunday night or something like that. And so on Thursday, if you would try some of these at home, between now and Thursday, we can have a discussion. And that'll be it.